along the different directions X, Y, and Z. And you can do the same thing for B, and maybe you can calculate the dot product as I do here by rewriting A and rewriting B, and then you develop this product and you use the fact that X times X is 1, so that's going to contribute an AX BX, and X dot Y is going to be equal to 0, and so this product AX AY is not going to appear in the result on the other side. So I'm realizing that you are very familiar and experienced with all these, but we're going to be using the exact same math in a type of space that is just a bit different. And the reason for this is that in quantum mechanics, the states, you consider a system. So for example, last time we were talking about the Stern and Gerlach experiment. And if you think about one particle going through the device, if you had to describe the state of this particle, maybe you would describe the position and the momentum or the speed of the particle. But these aspects for now we are going to ignore. We are going to concentrate on the aspect that is measured by the Stern and Gerlach device, which is the angular momentum of the particle. And what we found is that as far as the angular momentum is concerned, the Stern and Gerlach apparatus for an electron, we make the measurement, and the outcome of the measurement had two possible values, which we said were plus 1/2 h bar and minus 1/2 h bar. And we're going to see exactly why it is plus and minus 1/2 of h bar. But each one of these states corresponding to different outcomes of the measurement, we are going to represent it by a vector. And that's a vector that is living in the vectorial space, that is the state space of the system that is being considered. And there is a notation that is somewhat different for these vectors, which is indicated here. And it is called a ket vector. The origin of ket is coming from the fact that we're going to form brackets, and ket is just the second part of the word bracket. It's not very. And so if we consider a particle, one electron, for example, that goes through this Stern and Gerlach apparatus, and that the outcome of the measurement is that the z component of the angular momentum is plus h bar over 2. We are going to write the state of the particle as being plus sub z in a ket, so a vertical line and greater than sign. And of course, there is a corresponding state which is minus sub z. And since there is no other possible outcome to the measurement of the angular momentum of this electron, it is clear that plus and minus sub z, they map the entire state space of the electron as far as we are restricting ourselves to the angular momentum of the electron. And so if the particle is in the state plus sub z, it is not in the state minus sub z. And that's something that we are going to transcribe by stating that those two vectors, they are perpendicular to each other. So here you see that I write, let me zoom in, I write the ket minus sub z. And here I write it kind of flipped, and we call that a bra. Okay? At this point, it's just notation, right? We're going to get into the mathematical definition of these things more specifically. And another requirement, which also will be justified as we work through this formalism, is that we're going to choose that minus minus, so the inner product between the minus sub z vector and itself, as well as the plus sub z vector and itself, they're equal to 1. Okay. So since the we identify that the state space is two-dimensional, and we are considering plus sub z and minus sub z as constituting a basis. That means that, for example, the electron that is going through the Stern-Gerlach device that measures the x component of the angular momentum can be described as a linear combination of plus sub z and minus sub z. Try my pen again, it still doesn't work. And that's going to be the case of any state of the electron. It will always be possible to write it as a linear combination of plus and minus sub z with two coefficients, c plus and c minus, which are essentially playing the role of ax, ay, and az up there in the more familiar case of vectors in the physical dimension space. Do you have any? And you are still with me, right? I'm not talking alone.
No, we can still hear you. I do have a just a minor, very minor question. So the textbook uses like a slightly different notation for the Ket and Bra vectors, where they put the z inside. That doesn't matter.
Yes. No, yeah, it's just I don't know. I'm used to. It's just habits, right? I'm just used to write. I'm just used to write like that. It's true that in the book they write minus z within the bra, within the Ket symbol, but that's it.
Okay.
In fact, you're going to see that since for traditional reasons, when discussing angular momentum, you're going to see that the z component is, we're going to use it in a spatial way. I'm going to end up not even writing that z pretty soon. I will just not write it. Okay.
Okay, thank you.
But yeah, please feel free to interrupt me at any time, especially since we are going through a video, and I cannot see you as I would if we were in a classroom, right? So I cannot read your attitudes, or I cannot detect anything from you unless you say something. So please feel free to interrupt me at any time. Someone was going to say something.
Yeah, I was going to ask, on that definition we were just looking at, where we have the Ket vector with phi inside of it.
Yeah.
If we were to change the phi to a plus or a minus, how would it affect the right side of the equation?
So for example, here.
Yeah.
So if you hide in your mind, I cannot use my pen, sorry. If you hide in your mind the psi here, you see that we have two unit vectors, plus and minus sub z, and what we're doing, we're saying, okay, since when we measure the z component of the angular momentum, we find plus or minus h bar over 2. That means that there are only two possible states, pure states from the point of view of angular momentum. And so these two vectors are sufficient to map the entire state space. So that if I form a linear combination of these two vectors by the means of two coefficients, c plus and c minus, I can reach any one vector in that vectorial space. And so in this specific case, I just give it a name, which is psi. So I will not have the freedom of saying, okay, I'm going to replace the psi by a plus sub z, as you were suggesting, because then it would just imply that c minus is equal to 0 and c plus is equal to 1.
That makes sense. Okay.
That's it. So although all this may look a little bit foreign, it is very similar to what you have been doing with usual vectors. The one difference that we are going to be discussing soon is in the fact that these coefficients, while when talking about velocity, momentum, accelerations, C plus and C minus, they were real numbers with maybe a unit attached to it, like meters per second or meters per square second or newtons or whatever. In quantum mechanics, these numbers, they're going to be pure numbers, and they're going to be complex numbers. But that's the main difference. Okay. Everybody's good?
Yep.
Okay. So we have this psi that is written in this way, and although I introduced the notation of the inner product already here, in order to better understand the mechanics of these coefficients C plus and C minus, we need to form the product between two states, which I already indicated here. But let's look at the case where you have two states phi and psi. So you see, just concentrate psi. You see that if I and that's important because I wanted to do the same. Let me try to activate my. It's very. I find that very frustrating. I'm going to try to sync my pen again.
I think to fix your pen, you just should reconnect it on Bluetooth. I'm not sure about that. But if it's unconnected in Bluetooth, that would probably be why it's not working. Yeah, it says it's not connected.
Oh, yeah, you're right. Okay. Yeah, but so I've done that several times now, and you see, now my pen is plugged in the side of the. You see my control panel here?
Yeah.
And it's not connected.
So if this doesn't work, I was reading on the internet, what you want to do is forget the connection and then reconnect the pen. But you can try that later.
It says it's connected right there, right?
Yeah.
Well, now it says
it does.
Oh, shit. So is it working now? Oh, it's working now. So what did I do to make it work?
Just reconnect to Bluetooth.
Oh, okay. Oh, thank you. I'm sorry. I'm just bad with these things. Okay. So then let's go to the. I'm getting disorganized with all this. Let's go to the problem. So we'll come back to this later. But let's practice a little bit with this. So we have this basis x, y, z, and we have what we discussed earlier is that one vector a we can write as a sub x hat plus b sub x plus a sub y hat plus a sub z z hat. And then if you are given a vector like this, and you wanted to just figure out what is the y component of this vector, what you would write is you would write a, and you will multiply a by y hat, and using the orthonormal property of the basis, you see that y times x is going to give 0, but y times y is going to give 1. Right? So this dot product is going to be equal to just a sub y. Right? You're clear with that? And so here it's going to be the same thing with these vectors. And for example, this psi that we wrote this way, if I were to multiply it on the left, with plus sub z. So I can replace psi by this expression, and you see that plus sub z multiplies plus sub z is going to give us 1, while plus sub z times minus sub z is going to give us 0. Or it's written here. And so the result of this inner product, dot product, is going to be just C plus. And so it works exactly in the same way as with usual vectors. Okay? And of course, if we could do the same thing with minus, multiplying psi by minus sub z, and through the same logic, we're going to obtain C minus. Okay? Now, this C plus or C minus, we could multiply them by plus sub z and minus sub z. And so you see that, for example, if I were to write psi, I could write plus times psi, which is the component of psi along the plus z ket, and I multiply this component by the ket plus sub z. So this is a number that multiplies a unit vector. And I can do the same thing here, where I have the component of psi along minus sub z that multiplies the unit vector minus sub z. So clearly, psi is equal to that. Is there any doubts or questions about this? Everybody's good? So now if I were to, you see that I have this ket psi here and here, so I can factor out the psi, and then I would be, I would find myself with just the ket plus sub z times the bra plus sub z. But here the order matters, right? It's important that plus sub z, the ket, is on the left side of plus sub z, the bra. And the same thing with minus, right? So we have psi that is equal to the ket plus sub z times the bra plus sub z plus the ket minus sub z times the bra minus sub z, multiplying psi. So psi is equal to something that multiplies psi. So that means that the something that I rewrote here is equal to the identity, right? Since I multiply psi by something and I don't get anything different. And this relation we're going to use many times. And it has a name, it is the closure relation. Is everybody good about that?
Why?
Oh, go ahead, Pierce.
Why does it equal 1 and not 2? If you said earlier,
because you see, I have this thing here is multiplying psi, right? And the result is equal to psi itself. It's not 2 psi, it's just 1 psi, right? So psi is really not changed by the action of this thing.
okay,
That's answering your question?
I think so, yeah.
Oh, shit.
Okay. Now at the same time, we could, so you see, so far I have only talked about really the ket vector, but clearly this is a vector as well. It's slightly different because it's a vector that is modified so that it can be combined with the ket vector so as to form a product that gives us a scalar. So this bra vector can also be written as a linear combination of the plus sub z bra and the minus sub z bra, but the coefficients C plus and C minus, they're going to be different in general. They're going to be different from the coefficients for the ket psi. So that's why I call them C plus prime and C minus prime. And exactly in the same way, I could multiply this psi. I could multiply it by the ket plus sub z on the right side. And you see that this ket plus sub z on the right side would combine with the bra plus sub z on the left side to form 1. While the ket plus sub z combined with the bra minus sub z on the left side would give us 0 because of the orthonormality property of the plus sub z minus sub z set. Okay. So using the same trick that we have seen before, we can extract the components of the bra psi along the bra plus sub z and the bra minus sub z. And we can use that now by just writing what would be the inner product of the vector with itself. So here I write bra psi ket psi, sorry, bra psi ket psi is equal to 1. And that's something, each time we'll have a state vector that has this property, we're going to say that the state vector is normalized. And is in this normalization condition between the bra and the ket, we can insert the closure relation. And again, the closure relation is that thing. That thing, it's a thing that does nothing, right? It's like multiplying by 1. So if you do that, you're going to obtain psi times the first term, the closure relation, times psi. Here's the bra, here's the bra, here's the ket, and it is bracketing this term. And I have psi times the second term in the closure relation, multiplying the ket psi. Now we can, using these definitions that we have here, 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 sorry, and here, we can rewrite this expression. We can rewrite as C plus prime C plus C minus prime C minus equals 1. So the normalization condition here, that is a property of psi that is independent from the basis that you are using to describe psi, is transcribed once you choose a basis, is transcribed in terms of the components of psi into this expression that we have here. And so I already told you that these numbers, C prime, C minus prime, C minus, they are complex numbers. And I also mentioned the fact that we want to have psi times psi equals 1, which is a real number. And the way to satisfy this is simply to choose that C1 prime sub plus, so C plus prime, pardon, is equal to the complex conjugate of C plus, and the same thing for C minus. So C minus prime is the complex conjugate of C minus. So that means that if psi is written, psi the ket is written this way, then psi the bra is going to be written the same way in terms of bras, but the components, the coefficients, are going to be the complex conjugates of the coefficients that appear in the expression of the ket. Any questions about this?
I have a quick question. You said that we generally require the bra psi ket psi to be equal to 1.
Yes.
What circumstances would it not be equal to 1?
let me get to the next point then, because I think that will provide the answer. So that, yeah, that will provide. Essentially, it's not going to be one when we don't care, but that's it. There is a postulate, and maybe I should comment on that word postulate. When you have been studying mechanics or electromagnetism or anything else in physics that is not quantum physics, you maybe that's not the way it's always taught, but in the ideas of physics, you start from very fundamental principles, and by applying these fundamental principles, you can reach very elaborate conclusions about complicated situations. In the case of quantum mechanics, things work quite differently, and there is no fundamental principles justifying the structure of quantum mechanics. And instead, quantum mechanics is constructed on a number of postulates which are justified by the fact that after the fact, it was noted that they are effective at predicting what is observed. But it's not like, so for example, I don't know, in mechanics, if you have taken 50, what is the name of that class? 5410 maybe, where you teach, where you study Lagrange mechanics, you have seen, for example, that there are very, very deep statements that you might have seen. For example, maybe you have studied that if a system is independent under displacements in time, then energy is conserved. Or if a system is the same, whether you move it to the left by 1 meter or to the right by a light year, that implies that momentum is conserved. You know that, you're familiar with that, the Noether theorem? Oh, you're not familiar with the Noether theorem? Amy Noether? Okay. So you're still with me, right?
Yep.
We're here.
So in mechanics, you have very, very fundamental principles from which everything unfolds. In quantum mechanics, you have a few statements that are justified only by the facts, but not by any fundamental mathematics. Or they have been chosen because they work. Okay? And there is no, at least there is no known or recognized fundamental principle that is underlying these ideas. And so one of the postulates of quantum mechanics that is justified by the fact that it is very efficient at predicting what is observed in the lab is known as Born's rule. And it goes in the following way. So still thinking about one electron going through the Stern and Gerlach apparatus, we have seen that the state of this electron, psi, for what concerns its angular momentum, can be described as a linear superposition of two states corresponding to the two possible outcomes of the measurement. And thus it turns out that these two...
I'm sorry to interrupt, but you stopped sharing
No.
your screen. I'm not entirely sure if you meant to or not, but we can't see what you're doing.
Right.
No, I did not mean to. Oh yeah, you're right. I'm sorry. I don't know how I did that. You see my screen again?
Now we can.
Yes.
Okay, sorry. Okay, so what I was saying, or what I was pointing at, is that the state psi can be described as a linear combination of two states plus sub z and minus sub z, corresponding to the two possible outcomes of the measurement of the z component of the angular momentum of the particle. And this superposition involves two coefficients, c plus and c minus. And the way these coefficients are interpreted under Born's rule is that they are, so first they are complex number, and their magnitude square is the chance probability for the electron to be observed in the state plus sub z. So you may feed the Stern and Gerlach experiment with in a state that is not plus sub z, that is not minus sub z. It's maybe a combination of both. Maybe it is plus sub x. Okay. And you make the measurement, and you will either observe plus h bar over 2 or minus h bar over 2. So you are either going to observe the electron in the plus sub z state or the minus sub z state. And that's an observational fact, right? It's not resting on anything more fundamental than that. It's just observed that way. And if you postulate that the chance probability for observing plus sub z is the magnitude square of the coefficient in front of plus sub z, and the same thing, of course, for the coefficient in front of the minus sub z, right? Their magnitude square of these coefficients will be the chance probability for you to observe the particle in either that state or that state. So you see, and I'm sorry, it's going to be very difficult to learn any of your names as well because we are not in front of each other. But one of you was asking about why this one, and here you have the answer. You see that with these coefficients, C plus and C minus, we are going to call them probability amplitudes, and their magnitude squares are probabilities. And the outcome of the measurement of the angular momentum of the particle is either plus h bar over 2 or minus h bar over 2, each one with its respective probability for a given state. And since there is nothing else that can be measured, that means that the sum of the probability to obtain plus sub z with the probability of obtaining minus sub z has to be equal to 1. And that's the reason why we like to normalize the vectors, the state vectors, to unity. So for example, we can even write, I don't like green as a color to write. Black. You see, using this expression, we can write plus sigma, that's going to be equal to, maybe I'm going to write brackets. I'm going to plus star, and I'm going to write the bra, so plus sub z, plus C minus star times the bra minus sub z, multiplying psi, the ket is C plus ket plus sub z plus C minus times the ket minus sub z. Okay. And so you see that when I multiply plus with plus, I'm going to get 1. So that's going to give C plus star C plus. Then when I multiply C plus, not C plus, sorry, plus sub z with minus sub z, I'm going to get 0. When I multiply minus sub z with plus sub z, I get 0. But when I multiply minus sub z with minus sub z, I get 1 again. So the second term is going to be C minus star C minus. And you see that this is just the magnitude square of C plus the magnitude square of C minus. And if you accept Born's rule, which just states that this number is the chance probability to observe the particle in this state, while this number is the chance probability of observing the particle in this state, then the sum of the two probabilities has to be equal to unity to express the fact that there is nothing else that can be observed. Is that making sense? And do you have questions?
That makes sense. Personally, I only had like one question, and it kind of has to do with some of the material later on in your notes in the book, right? It mentions that each one of those, the C plus or the C minus, there's the chance probability of the particle being in that state, and both of them added need to equal to 1. But the one thing I'm having a little bit of problem with is that it states that they don't necessarily each have to be, or like one C plus or C minus doesn't have to be like half and half. They can be like, because I think in the book they do an experiment of like 100 particles, and they say like 45 can be in one state, and like, I don't know, 50 or whatever could be in the other state, and it doesn't have to be 50-50.
No, it doesn't. No, it does. No. So okay, we can take an example.
I guess my question was like, when do we know that's the case and when not? That's what I was getting confused on.
So you could very well have C plus square equals 3/4, and C minus square equals 1/4. You see that the sum is equal to 1.
Yeah.
But if you prepare your 100 particles in this state psi, and you measure each one of these particles, well, for the first one, you will have 3/4 of a chance to observe plus h bar over 2, and only 1/4 of a chance to observe minus h bar over 2. For the second one, you will have the same chances, and for the third one as well. But although all the particles are prepared in that same initial state, the outcome of their measurements will be just driven by probabilities, which are 3/4 and 1/4.
Okay, so I guess it's just random. I guess I was just wondering.
It's random. It is so, and you're going to see. We're not done covering all the aspects of quantum mechanics, right? But you're going to see that quantum mechanics is entirely deterministic, except when it comes to measurements. And at the instant when you make the measurement, that's when randomness appears.
Okay. Thank you.
But it's a very important question. Let's say, so you have prepared your 100 particles in this state with coefficients which are such that their magnitude squared are equal to 3/4 and 1/4. And you measure the first particle, and let's say you find plus h bar over 2, so you satisfy this probability. And the second particle, well, you get lucky and you get minus h bar over 2. There is another kind of postulate of quantum mechanics, which is that the state of both particles was still the same. The fact that you got different measurements doesn't mean that there was something preceding the measurement that was different between those two particles. Those two particles might very well have been the exact same state. Just at the time of the measurement, there was something truly random that happened, that led to the outcome of the measurement being plus h bar over 2 or minus h bar over 2. That's good?
Yes, thank you.
So it's like, for example, if you, I don't know, when a magician has a deck of cards and he presents the deck to his audience, and he says, please choose a card at random. And in fact, what happens is the person chooses a card in ignorance of what card it is. But the card that the person picks is already a king of hearts before the person has made the choice. There's nothing that changes in the card. Right? In quantum mechanics, it's different. you may use a Stern-Gerlach apparatus, and the magician tells you, okay, pick up an electron with an angular momentum plus h bar over 2, and you're going to grab that electron, you're going to measure it to have plus h bar over 2, but before the measurement took place, the angular momentum of the electron was not defined to be, or was not necessarily defined to be plus h bar over 2 or minus h bar over 2. There's something that happens at the time of the measurement. While in the case of a set of cards or a dice on the table when the light is off or when it is in the cup, you know, that you are used to shake the dice. At the time you look at the card or at the time you look at the dice, there's nothing that happens. There's nothing that changes in the state of the card or the state of the dice. And that's where there is a huge difference between classical physics and quantum physics. Now, it's also possible that instead of these numbers, we could also prepare the electron in a state where the magnitude square of C plus is 1 and the magnitude square of C minus is 0. In which case, if all your particles are prepared in that state, of course, all your measurements will result in plus h bar over 2, and none of them will result in minus h bar over 2. And that's the only case, in fact, where you could tell ahead of time what is going to be the outcome of the measurement. But if the state of the particle is a superposition of these two states, plus and minus sub z, then there is no way to predict what will be the outcome of the measurement because it will be fundamentally random as far as we know. And it's more than as far as we know because it's even proven that there is no other information in the state of the particle than the state of the particle. Okay? Are you satisfied? Am I alone?
No, that was good. We can.
That's good.
Oh, you're good. Okay. Okay, I'm sorry. You have to reassure me once in a while because when I hear silence, I feel maybe I lost everyone or something. I need to be more confident. Okay. Next page. So and we can apply this to to the discussion of the Stern-Gerlach experiment. Maybe I reversed things a little bit, but let's say you have a first Stern-Gerlach device that selects particles to be in the plus sub x state. And these particles, you run them through a second Stern-Gerlach experiment that is going to measure the z component of the angular momentum. So again, the outcome of the measurement is going to be either plus or minus h bar over 2. So that means that the state in which the particles were prepared can be expressed as a linear combination of two states corresponding to the two possible outcomes of the measurement, with each one coefficient being such that its magnitude square is equal to 1/2, because that's what we have observed in the experiment, where we have considered x and z to be in a perpendicular direction. Okay, so that tells us that C plus star, C plus, as well as C minus star, C minus, are equal to 1/2. Now, that means that C plus, just by itself, is equal to 1 over square root of 2, right, which is the square root of 1 over 2, multiplied by some phase factor exponential I delta sub plus. And the same thing for C minus. So that means that the state plus sub x can be written as exponential I delta plus by square root over 2, square root of 2, times z, plus sub z, plus exponential I delta minus, another phase, divided by square root of 2, multiplying the ket minus sub z. And this plus and the delta plus and delta minus, we don't know what they are, but they really define the state. So that's another postulate of quantum mechanics, which is that these coefficients, C plus and C minus, they are complex numbers, so they can be defined by their magnitude, which in this case is square root of 1/2. And they have to be multiplied by a phase, which is exponential I delta plus and exponential I delta minus. Now there is something that is interesting, which is once you have written that state, you could always factor out exponential I delta plus, for example, in which case that would be multiplied by just plus sub z, with just 1 over the square root of 2, and exponential I delta minus minus delta plus times minus sub z. And you see that then we can measure anything we want, like we can measure Sz, for example, again. And this is going to give us, so this expression gives us the probabilities of obtaining either plus or minus h bar over 2 in the measurement of Sz. But you see that this phase factor is not going to change these probabilities. So that means that's an information about, so you take a state, for example, this state, and you can multiply it. Let me take a pencil. Maybe I have a state psi, and I can, if I know the expression of psi in terms of plus sub z and minus sub z, I can predict what the different probabilities of the different possible measurement outcome. And then I could change this state to another one. Maybe I can call it psi prime, which is exponent I alpha, some angle, times psi. That's not the same state, right? Because it doesn't have, in the state space, it does not have the same coefficients on a given basis. So it's not the same state. However, the probabilities that I will predict based on psi or based on psi prime are going to be the same. Because when I take the magnitude squared of the coefficients on the basis that I'm using, that exponential I alpha is going to be multiplied by exponential minus I alpha. And so it's going to cancel out. So there is a freedom in the definition of the phase of a state. However, you see that there is something that remains when I factor that out, this exponential I delta plus. There is something that remains inside the expression here, and that's an exponential I of the difference of the phase between the two terms plus sub z and minus sub z. And so that difference, so the relative phase between the two components, that's something that that is important. That changes the type of predictions that we're gonna make. While the global factor in front as a phasor is not going to change anything to the physics that's going to be observed. You're good? Any question?
So later on, we'll discuss more about like why we need to know the phase. Is that right?
Yes, and you remember last time we talked about, maybe I can go back to it actually. You remember us discussing this experiment, and we understood here that you had this separation, and I commented on the fact that here there was an interference. And you remember when you studied optics and interferences, you remember that the relative phase of two beams of light is what decides whether you have constructive or destructive interferences, right? And so that's the same thing here. And that's why I was stressing that what is important is that this phase factor here is going to be what decides of how that one state is going to interfere with another state. Okay.
Great, thanks.
Okay, and at this point, maybe I'm kind of repeating myself, so it's going to be the same idea. So let me just summarize all this, and then we can move back to the problems. So the first thing, I guess, is that the quantum state is specified by a vector, which we call the ket vector, and the notation is like that. And associated to this ket vector, there is also a bra vector, which is noted this way. And the bra and the ket can be combined to form a product, which is a complex number, which is written in this way. And you can convince yourself that the product psi phi is the complex conjugate of phi psi. Should I discuss that, or is that clear by itself? You're good?
No, could you please discuss that, the phi and the psi? Thank you.
Okay. So let's take expressions. So maybe I have psi that is equal to a plus, maybe a plus a minus minus. And I have phi that is equal to b plus b minus minus. Okay. Now we have seen that phi is going to be equal to b plus star plus b minus star minus, right? So when I form the product phi psi, I'm going to have b plus star plus, that multiplies a plus plus, which is going to be just b plus star a plus. Right? Plus, then when a b plus star plus multiplies a minus minus, I get 0 because plus and minus they are orthogonal. Right? So the next thing that's going to be non-zero is going to be b minus star minus multiplying a minus minus, which is going to be equal to b minus star a minus. So this is the product phi psi. Now, if I were to write psi phi, I would proceed exactly in the same way, but using psi as being a plus star plus a minus star minus, right? And then I will multiply this term with this one. And that would give me a plus star b plus, and then I would multiply this term with this term, but that would be, then I would multiply this term with this term, but that would be 0. And then I would have this term, multiply this term, which would give me just a minus star a minus b minus. B minus. And so you see that you go from here to here by doing a complex conjugation, right? So, okay, maybe the thing that I should remind you is that Z1, complex number Z1 times a complex number Z2 star is equal to Z1 star times Z2 star. Is that answering your question? So if I essentially if I take the complex conjugate of this, I obtain that, which means that this is the complex conjugate of that, and that is the complex conjugate of this.
Yeah, very good. Thank you, Professor.
Okay. Okay, so states are specified by kets that are associated with bras. This is going to be called a probability amplitude. So if you have a state that is prepared in the state psi, and you measure something whose outcome corresponds to the state phi, then phi psi is going to be the probability amplitude for the particle in state psi to be found in state phi. And associated with this probability amplitude is a probability which is obtained by taking the magnitude square of the probability amplitude. And that probability amplitude is unchanged under the transformation from psi to psi multiplied by some phasor. Now, when we measure something, we talk about measuring an observable. It's something that can be observed, right? And for each of the possible outcome, A1, A2, A3 in this case, so far talking about the angular momentum of an electron, I just told you that there were only two possible outcomes, but you have other things that you can measure that have more possible outcomes. To each of these possible outcomes corresponds different quantum states for the system that is being measured. And we're going to see that these quantum states, each corresponding to a possible outcome of a given measurement, they constitute an orthonormal basis, which I can write by saying that AKAL bracket is equal to delta KL, where delta is the Kronecker symbol, which means that this is equal to 0 when K and L are different from each other. So when I'm considering two different vectors here. And this is equal to 1 when K is equal to L, which means that I'm considering the same vector on both sides here. The other thing that we have seen is that once you have a basis, like this one, you can express any state of the system as a linear combination of these vectors in the basis. So here you see the vector, one of the vectors in the basis, and here are the components, the amplitude of psi in the component A sub n. And then when you just sum over all these states, you get the state psi. And I told you that this is known as the closure relation. Okay. And having a state normalized ensures that the sum of the probabilities of all the individual possible measurement outcomes is equal to 1, which is expressed here. And oh yeah, maybe I skip talking about the expectation value. So once if you have the possible outcome of the measurements are an, and you multiply these an by the probabilities to get them, and you sum over all the possible possibilities, then you get the mean value, right? Which is called the expectation value. Or you could calculate also the expectation value of the square of the observable, which is just the sum of the squared outcome of the measurement multiplied by the probability of each of these measurements. And the reason why this is interesting is that it allows you to calculate the standard deviation of the outcome of the measurement as being the square root of the expectation value of the difference between the outcome of the measurement and the mean measurement, which you can rewrite as the difference between the expectation value of the square of the measurement minus the square of the expectation value of the measurement in a square root. Any questions about all these? I think it's going to be clarified by playing with problems.
Professor, I have a question. Will we talk about the wave function collapse, and is that what it's showing there?
Yes, and this wave function collapse is one of the postulates, which, let me go back to this page. You were there on Monday?
Yeah.
You see here, for example, we bring a particle that is not in the plus sub z or minus sub z state. So that out of this first Stern-Gerlach apparatus, there are particles arriving here and particles arriving there, and they are blocked. So clearly, this first measurement amounts to a collapse of the wave function. Here you have a superposition of plus sub z and minus sub z, while here you just have plus sub z, and it corresponds to the outcome of the measurement being plus h bar over 2. And actually, if we repeat the measurement, then we just obtain plus h bar over 2, confirming that the particles here, they were in a pure state of angular momentum along the z component, or along the z axis.
Very good. Thank you,
Yeah,
Professor.
that makes sense. But we'll come back. We'll come back to that. That's a postulate that is named after von Neumann. It's a von Neumann postulate.
Awesome. Thank you.
Any other question? Should we? So we have I'm sorry, I've been slow again this time. This time it was not because I talked too much. It was because I had technical problems. Is it interesting to finish this problem, or are you good with it?
Can we please finish it?
I'm interested. Yeah.
Okay. So what I like to do is have you tell me what to write. So is there anyone with questions regarding that part, or is everyone clear now?
I think that the derivation of the moment of inertia and then plugging it for the angular momentum is pretty clear for me.
Okay, so we can move on. So how do you calculate the magnetic moment then?
So it would be like the current times the area.
Right. So let me write that. So let's call that the current. I'm going to use a little I so as to avoid confusion with the I that I already used for the moment of inertia. Times the area. Maybe we can write the area of the disk right away as pi. So good. So capital R, pi r squared. Okay. So how do we write I?
So I was thinking of writing it as a charge over time, so Q over T.
Yeah. So that's the charge that is accumulated on the edge of the disk by r squared, and we need to divide by the time it takes for the disk to complete a rotation.
And I think the way I was thinking of it was time is equivalent to distance over velocity. So I was thinking of substituting those terms.
So you see that here we have expressed the angular momentum as the moment of inertia times the angular velocity. So how much time does it, given omega, how much time does it take for one rotation to be completed?
2 pi over omega.
Yeah, so it's 2 pi over omega. What you were saying was correct, right? But since we are dealing with something that rotates, it's easier to talk about angles compared to talking about velocities in meters per second. Okay? So the pi simplify, and we end up with q r squared over 2 times omega. And so then we can do the ratio, and we see that mu over L is going to be equal to q r squared over 2 divided by, what did I find? M r squared over 2. So we just end up with q over m. Okay? Everybody's
good.
good with that?
Yeah.
Yeah,
Okay.
looks good.
Any question about this?
Nope.
No, that's simple. Huh? You're familiar with that. Maybe let's start practicing with this one. So here we are told about a three-dimensional quantum space for which we are given a basis of 3 vectors, right? 1, 2, and 3. That is given in the form of 3 kets. And this basis is mapping a state space that is named S, okay? And we are given 2 ket vectors, for which we have these expressions in the given basis. And the first question is asking about the norms of A and B. And it is asking us to write a normalized version of these vectors.
Is the norm in this space just going to be like the square root of the sum of the squares? Just like it would be for a vector in Euclidean space?
Okay, so okay, let's do that. So tell me what to write.
So was the first question the norm?
Yeah.
Yeah. So for the norm of
Let's say the norm A.
Ket vector A, would you write the square root?
So what should I'm writing. I should not write. Yeah, the square root. Okay. Yep.
Yeah, the square root. 2 squared.
What do you?
Can you hear me?
Okay. So yeah, I hear you, but I have a hard time understanding where you're going. So you want me to write the square root?
Is what? It the square root of the coefficients of?
So tell me what
that we're given in A. So because we have 2i and negative 2i.
Uh-huh.
So would it be the square root of the sum of the squares of each of those?
I would like you to tell me what they are.
So 2 squared plus I squared.
Okay, so 2 squared.
Negative 2i squared.
plus I squared plus negative I squared.
Negative 2i?
Oh, 2i, sorry.
That's all under the square root.
So is there anyone who disagrees with this?
I kind of disagree.
Can you explain why?
We said that for these ket vectors to be normalized, that the bracket, so
yes,
A bra time, well, the inner product of bra A and ket A should equal 1.
Right. So here we will just ask at first to calculate A, and the square root of that is going to be the magnitude of A. Right? So, okay, the coefficients are 2i minus 2i. So it's going to be 2, 1, minus I, 2. I forgot it's plus 2i. And so here, I just wrote the bra A. And the important is that you see, instead of I wrote minus I. Instead of minus 2i, I wrote plus 2i, because to construct the bra A, from the ket A, I need to replace each of the bras, each of the kets of the basis by the corresponding bras, and the coefficient, I need to replace them by their complex conjugates. Okay, and now I have written the bra, I can write the ket. Which is going to times 1 plus I times 2 minus 2i times 3. You see the difference with the first person who was offering an answer? You shot straight to making the sum of the squares, which is the way you are trained to think when dealing with a physical space like around where we are. While here in a complex space like this one, so it's complex because the coefficients are complex, you have to replace the squares by the magnitude squares. So multiplying the coefficients by the complex conjugates of the coefficients. Okay. So then we are told in the question, we are told that this basis 1, 2, 3 is orthonormal. So that means that 1 times 1 is going to equal to what?
1.
1, while 1 times 2 is going to be equal to
0.
0, right? So that means that when I distribute this product, I'm going to have 2 times 2, which is 4. That multiplies 1 times 1, but I don't need to write that, it's 1. Then I'm going to have minus I times plus I, and that's going to be plus 1. And then I'm going to have plus 2i times minus 2i, which is going to be plus 4. Okay. And all this is 9. So that means that in order to have, what should I do? So I have this A, that is, since the bracket AA is equal to 9, how should I rewrite a new A such that the norm of A is equal to 1.
You just put it over 9.
So 9 is.
Oh, 3.
Wait, yeah, 3, right? Okay. So it's going to be so the answer is going to be 2 over 3 times 1 plus I over 3 times 2 minus 2I over 3 times 3. Okay? Any question?
I have a question.
Yep.
So with the first,
Hello?
hi. With the first term in the, basically like, I don't know how to word it, but shouldn't there be a negative in front of the 2 on the first term?
Here?
No, the other one.
Here?
Yeah.
Look, you see that A is equal to 2 times 1 plus I times 2 minus 2I times 3. And if I wanted to write the bra, A, I'm going to write the bras, 1, 2, 3. And I'm going to multiply each one by the complex conjugate of the corresponding coefficient. So the complex conjugate of 2 is 2. The complex conjugate of plus I is minus I. And the complex conjugate of minus 2I is plus 2I. Right? So the 2, you see the sign does not change because it's a real number, and the complex conjugate of a real number is the same real number.
Yep, got it. Thank you.
Okay. Okay, so let's do B. So I'm going to write BB. But maybe we can go. We don't need to write all the steps now, unless you you feel like we should. But you see, it's going to be minus I times I plus 4 times 4 plus 1 times 1. Right? So minus I times I is plus 1. 4 times 4 is 16. So 16 and 1 is 17. I'm surprised that I did not choose something that was more friendly than that. But 1 times 1 is 1, so that's 16, 17, 18. So this is going to be 18. Any question about, everybody agrees with that, or?
Yeah, looks good.
You're good? Okay. So that means that if we want to have a normalized form of B, we're going to write B, we're going to replace B by a new B that is normalized. That is 1 over square root of 18. So that's 1 over square root of 2. 1 over 3 square root of 2, I guess. Multiplied by, okay, what do we have? I, 4, and 1. So I times 1 plus 4 times 2 plus 3. So this is the normalized version of B. Okay? Shall we move to the, do we have time, or no, we still have time. Let's calculate BA. So tell me what I should write.
We can just use the complex conjugate of B, right? And then multiply it by A.
Right. So I'm going to write. I can write that. So I'm going to write 1/3 square root times minus I 1 plus complex conjugate of 4 is just 4. Complex conjugate of 1 is just 1. Multiplied by, I forgot what is A, but that's 2/3. Is 2I minus 2. Okay, so that gives us 2 over 9, oops, over 9, square root of 2. And we have, okay, minus I times 2, that's minus 2I. We have 4 times I, that's plus 4I. And we have 1 times minus 2I, that's going to be minus 2I. Right, so that's the complex number. So that minus 2 plus 4 minus 2 is equal to 0. So when we have two vectors whose inner product is equal to 0, we say that they are mutually orthogonal. So let's do one more, if you're okay, let's do one more question. And we'll do the next ones next time. Maybe next time we will start with these questions and then keep moving on the notes, okay? So the question is, find and express a ket vector C such that ABC is an orthonormal basis. And you see that what we just obtained is that AB, they are orthogonal to each other. And here and here, we have made sure that they were of norm 1. So what we need to find is one vector C that is of unit norm and that is also perpendicular to both A and B. So how would you proceed to solve that?
If they were normal vectors, I'd want to do the cross product of A and B, but I don't know for sure if that works with ket vectors.
So repeat that.
If like to get orthogonal vector from two other vectors, you would just take the cross product of those two vectors. I don't know if I can do that with ket vectors.
No, so you see, okay, think about think again about the stealth experiment. We have said that we have two vectors, for example, plus sub z and minus sub z, and these two vectors, they are sufficient to map the entire vectorial space. So it's a two-dimensional space, but the coefficient of that space, the coefficient of the components, the components of these vectors in that space, they are complex numbers. So to specify one vector, you need 4 numbers. So it looks like a two-dimensional space, but it's kind of a 4-dimensional space as well. Right? So the cross product is not gonna help us. So the only thing that we can use is, you understand why I'm saying that?
Yeah, I think so.
You see, in the case of the spin of the electron, so the angular momentum of the electron, everything looks like a two-dimensional space. In a two-dimensional space, there is no space for your right hand. And then you think a little bit more and you say, well, it's a two-dimensional space, but each of the coordinates, once I've chosen a basis, is a complex number. And so you find yourself in a 4-dimensional space. And your hand can fit in a 4-dimensional space, but your hand itself is not 4-dimensional. So you cannot construct I mean, there are ways to go around that, but we cannot really construct a cross product. Okay. So the only thing we can use is the inner product. You still see my screen because my tablet fell asleep.
It just stopped.
So that's what happens. Okay, so each time that happens, I need to go back to Zoom and start broadcasting. So how would you proceed?
So I remember, like, in the textbook, it mentions that, like, when they tried to find another, like, orthogonal vector by using the experiment in the z direction, the z device, they say that, like, the x direction could just as easily be the y direction. So it mentions that in order to express, like, another direction, we can use a superposition of our initial vectors. Is that
okay? But so you see that this problem, this exercise here is very abstract, right? It's not, there is not much physics in it. It's an exercise so that we play with a new concept that we have introduced. And so we are asked to find a vector, and this vector is in a space for which we have a basis. Right? The basis is this one here. And we already have two vectors, A and B, for which we have representations given in these spaces.
So I guess, so I guess the constraint that we have for C would be that it needs to have an inner product with A of 0, an inner product with B of 0, and it needs to have a norm of 1. So
exactly.
From there, we can develop 3 equations to determine the 3 coefficients that it contains.
Right, because we already know that A B is equal to 0, and A is equal to B is equal to 1. So if we find C that satisfies these properties, then the set ABC will be orthonormal. So in practice, how do you do that?
We can just possibly assign all the values for C as like C1, C2, and C3, and then we'll just have 3 equations and 3 unknowns.
Yeah, right. So we can write that C is equal to C1, 1, plus C2, 2, oops, plus C3, 3. And then it's just a matter of substituting this expression into this expression, and then into this expression, and in this expression, and make everybody happy. Okay, so maybe you can start playing with that. I see it's 4:59 now, so maybe we should stop. And we'll go over it next time. I apologize again for the complications at the beginning of this class. Hopefully, I will be more skilled next time with this. It will be less difficult. Okay, so you spend some time looking at this problem. You can keep moving down the list of questions as well. There are a few more questions that you can try to look at, and we'll start with that next time before moving to the next topic. So you should also look at the next set of notes that are available on the Canvas page, and I will post what we have done together today on the Canvas page. Just one comment. Today, I was going over the notes, kind of reading them and waiting for you to interrupt me. You will have to tell me if you find that helpful or not. What we could also do is we could look at the notes together and just go to the points where you have questions, so that maybe it's quicker. But I leave that up to you. Okay, if you don't tell me anything, I will just keep going through the notes. But if you want me to jump to some specific points in the notes that you will have read anyway, we can do that to be more efficient. So sometimes reading the notes also gives me the chance to make comments on maybe a bit of a sense. But that can be useful. So I do as well. Okay.
I had one question. On the class outline, it said today there's a quiz.
Oh shit, I completely forgot. I completely forgot. I have written the quiz yesterday and I forgot to post it and set it up. I will move the quiz to Monday. Okay, so maybe next week we'll have 2 quizzes. I made a mistake. I completely forgot.
All right, cool.
But the quiz will be that type of question. So, okay.
Similar to the ones we just worked out.
Yeah, the same type.
Oh, okay, cool.
Okay, so we'll do that. I'll set that up Monday, and the idea is that you will have to answer the questions, and then post your questions by the next evening, midnight. Post your answers. So. Okay, so stop broadcasting. I see that I still have 29 people in this meeting, so thank you for being there and being patient with me. I hope you will have a pleasant weekend, and I see you on Monday. If you want to stay for any extra questions, I'm happy to stay longer.
Thanks, Professor.
Thank you.
Thanks.
Thank you.
Thanks.
Thank you, Professor.
Thank you, Professor. I think that this worked a lot better